from the equation to the direction.
Yeah, so thanks for the introduction and also thanks for the invitation. It's definitely a great honor to be here at this special occasion celebrating Jeremy Costello's work. Yeah, so I will talk about the convergence of the KPZ equation. And let me give you the online. Okay, yeah, so here is this outline. There will be two parts. The first part, I'm be talking about the convergence, especially from a dynamical point of view. And then from the unfortunately, this perspective is actually incomplete. So in the second part, I'm going to tell you what is known and what remains to be done. Okay, so here is this celebrated precision equation. And to solve this equation, we need an initial condition. And among the initial conditions, the narrow wedge one is the most important one. And then one of the major directions is to study the large time asymptotics. So here's this pioneering work. Some of them are in the physics community. And they all independently show that if you look at this one point at the origin, then the height converges to this tracery William GE. Yeah, and then a breakthrough after independently by these two groups shows this convergence of this space-time process. So if you scale this space and time in under this KPZ scaling, it converges to the so-called KPZ fixed point, which was constructed also by Jeremy and Konstantin and Daniel. Okay, so yeah, so what am I going to do today is to introduce this dynamical point of view. So here is this our KPZ equation. And we're going to view this as a random dynamics. So we're gonna begin with this initial condition. And then after you evolve this initial condition through this dynamics, we're going to get this height function. So as we saw earlier, if we do the 1, 2, 3 scaling, we're going to get a KPZ fixed point, right? So naturally, we may wonder the following question. Because we do have a dynamics here, what happens to the dynamics itself? So it's very tempting to just to apply the 1, 2, 3 scaling to the dynamics itself. So we wonder whether there's some nice dynamics here, and then that can give us this KPZ fixed point after give you see the initial value. And we can do this like a very natural attempt, which is to scale the equation. So on the top, we have the equation and then the solution. On the left-hand side, if you scale the solution, and then on the right-hand side, correspondingly, you can scale the equation, and this is what you will get. So if we send capital T to infinity, we get a KPZ fixed point. Then on the right-hand side, somehow the noise term disappears. But this cannot be right because we know that the KPZ fixed point is a continuous time, continuous space Markov process. So we are not expecting a deterministic PDE in the end. Okay, so what went wrong here? So why the noise here disappears? Is there another meaningful way to make sense of this dynamic still? So yeah, so because what actually happens here is even the strength of the noise is shrinking to zero, but the influence of the noise on the solution is increasing, and in a way that eventually the solution is still stays order one. So there's this trade-off between them. Okay, so now let's take one step back. If we want to understand the convergence of dynamics, which tells us how different initial value problems evolve at the same time. So why don't we consider these initial value problems to begin with? Okay, so this is the multiple initial value problem for this PDE. And thanks to the relation between this KPZ equation and then the stochastic heat equation, there's this fundamental solution. So there's a 4-parameter field which encodes the correlation or cause all of these initial value problems. And this fundamental solution also has a very nice statistic mechanics interpretation, which is the directed polymers. Yeah, so if you consider this stochastic heat equation with this delta initial condition, and then by the Feynman-Cass formula, you can write down in terms of closed form, and then by taking the logarithmic. In the physics language, this is called the free energy. So we will be also referring to the solution, the fundamental solution of the KPZ equation as the free energy of this continuous directed polymer model. Okay, so yeah, let me emphasize one more time on the role played by this fundamental solution. And then here's the main result. So if we consider the scaling of this fundamental solution under this KPZ scaling, it converges to the so-called directed landscape. And a direct corollary is that if you consider multiple initial value problems and then consider this 1, 2, 3 scaling, they converge jointly to the KPZ fixed point, all driven by the same directed landscape. Okay, yeah, so now, yeah, so there are just a few brief remarks on the directed landscape. It was constructed by the Wagner, Altman, and Bragg. And it is itself a central object in the KPZ universality class, and also other important statistics are also encoded here. For example, the Tracy Wiedemann GUE is the 1 point statistic here, and also it's if you vary the spatial variable, you get every 2 process. And we can also put the previous convergence result in the same framework. So the 1 point convergence is 1 point convergence to the direct landscape. And also one special case in Costa-Sakar and Bragg is that if you only vary one space time point, then you get this convergence. And our result is just the convergence of this in the full parameter regime. Yeah, so that is the main result. Now let me tell you what goes into the proof of this result. Remember, when we look at the random dynamics picture, the noise thing that if you just naively scale the PDE, the noise term goes away. So that means that the white noise is probably not the right way to keep track of how it drives that solution. And then naturally we wonder, is there a more regular way to keep track of the information we need from the environment, such that it behaves nicely under the KPZ scaling. And here comes the KPZ line ensemble. You can view it as the KPZ line ensemble as the image of the geometric RSK of the white noise. Yeah, so now let me tell you in detail what the KPZ line ensemble is. So here is this continuous directed polymer picture we saw earlier, and then we are going to go to the multi-layer regime and then get the KPZ line ensemble. This is just the solution to the stochastic heat equation when you take log, and then this is the free energy, and then I'm going to put a index 1 here to emphasize this is a single curve case. And then if you go to the multi-curve regime, this is what you are going to do. So we're going to explore. Yeah, so what we're missing before is just exploring the environment using one single Brownian path is not enough. It doesn't give us enough information of the environment. So I'm going to explore more. If you use 2 paths here, the actual energy you gain here is recorded in this X2, the second curve. And then we keep doing this, then we will get to this line ensemble. And then this is also introduced in this work about Connor Warren in the context of multi-layer stochastic heat equations. And then Corbin and Hammond took a different perspectives on the Gibbsian line ensembles. And then and then this is the KPZ line ensemble. It is a 1 parameter family. So for each time t, you get a Gibbsian line ensemble. And also, indeed, the KPZ line ensemble scales much nicely under the 1, 2, 3 scaling. And that convergence is obtained by combining these works. Yeah, so the first one shows the tightness and also limiting Gibbs property. The second one independently shows the convergence of top curve, and then there's characterization result by Evgeny and Konstantin, and also another strong characterization by Amor and Jiayang. Okay, so this is how the array line ensemble looks like. We have already saw this quite often by the two my following talks by Amor and Duncan. Okay, so yeah, so the key point here from the array line ensemble for my talk is that we can have a deterministic map to go from the array line ensemble to the direct landscape. So we can construct a direct landscape from the array line ensemble. Now we have the main ingredient here. So this is what we want to show. We want to show the convergence of the fundamental solution of the Gibbs equation to the direct landscape. And what we have here is this convergence of the line ensemble, which keeps track of the information. So we should be viewing that the every line ensemble is a driving force for the direct landscape, and the KPZ line ensemble is a driving force for the fundamental solution of Gibbs equation. And then there's this construction by the DOV paper from every line ensemble to a direct landscape. Naturally, we wonder if there is similar construction on the KPZ equation side. And this is what we apply in this paper, and use that result, we can apply this convergence. So this is the framework of how we get this convergence. Now, let me put this into this bigger picture, the random dynamics picture. So yeah, so this is the first part of my talk, which is about this convergence. And then for the second part, I'm going to focus more on this random dynamics side. So you can see that this arrow here is a dash arrow. That means it's incomplete. So I'm going to tell you what is known here and what remains to be done. So yeah, I wonder any questions before I move to the second part? Okay, yeah. So now let me look at this picture. What this is doing here. So we have this white noise, and we can solve the KPZ equation and get a fundamental solution. And what this procedure is doing here is a factorization. We factorize this procedure of solving the KPZ equation into two steps. The first step is to transform the noise into the KPZ line ensemble, which is the new driving force. And then we are going to construct we are going to try to construct the fundamental solution from the KPZ line ensemble. Let's see how much we know about that. Okay, and there are also nice interpretations of this procedure. So this part is the free energy, and then this from the white noise to the Gibbsian line ensemble is a variant of the geometric RSK. And yeah, and then we can view this diagram here as the following isometry as mentioned by both Amor and Duncan. So what you can do here, you can view the left-hand side as solving the KPZ equation, and then view the right-hand side as doing this is the construction of KPZ line ensemble, and then you run the Dirac polymer on the KPZ line ensemble. And yeah, so and now I'm going to tell you what we can do here. Yeah, so to explain what is actually going on, I'm going to first introduce the semi-discrete polymers. And what you see here is just this apparatus is a polymer path traveling in this environment. And then the way we associate the weight is as follows. So you look at this specific path, and then there are 4 levels, and then it travels in each level and then collect the weights respectively. So for example, the weight it collects on the 4th level is the increment from this point to that point, and so on and so forth. And then this is the total weight it collects along this trajectory. And then this is the semi-discrete polymer free energy. What you should really think of this as the energy cost for this particle to move from this bottom left point to the top right point when traveling in this environment. And this is exactly in the language of the free energy, the log of partition function, so in the statistical physics point of view. Yeah, so this is what we have. So you can, this XT here is a KPZ line ensemble, so you can go from the KPZ line ensemble to the fundamental solution of the KPZ equation. So, but there's always a but. So under this technical assumption, so we cannot get to this construction unless we have this estimates on the polymer energy across the KPZ line ensemble. I'm going to tell you more about how to think of this. Yeah, so any questions so far regarding this relation?
Is star proved?
Go back there. Yeah, so in terms of yeah, to the theorem, so it is proof, but it is proof that under this condition. So the theorem is like if you have star, then this equality is true.
I think the question is star.
Yeah.
Oh, is it star proof?
Yes.
That's what I'm going to tell you. Unfortunately, no. So the short answer is no.
But this is a statement about just the KPZ line ensemble, correct? The star equation.
That's right. The star is solely about the KPZ line ensemble.
So it's either true or false.
I believe it's true, but I
No. But my point is you don't have some parameters in the model that you, for some ranges it may be true and for some it may be false. It's either a true or false statement.
that's right.
Okay.
Yeah, and I do
I'm just making
believe,
sure I understand. It's not really.
and I do believe it's true, and I hope I can convince you in a few minutes.
Okay, sure.
Okay, so yeah, so this is the KPZ line ensemble. Let me, because I'm going to use it in a few minutes. So let me also draw it to on this side. Okay, so this is how people typically draw the KPZ line ensemble. And for the KPZ line ensemble, there are two things that are relevant for today. One is the Gibbs property. So yeah, I'm going to just to use the second curve and third curve to as an example. So suppose we fix a region A from B, and then we erase part of it. We're going to do a resampling such that we can recover the law of the KPZ line ensemble. And the way the resampling is as follows. I'm going to call this H1T, H2T, H3T, H4T. Okay, so, and then the law of the resampled curve, just within this window for this second and third one, with respect to two independent Brownian motions, I just write TB is proportional to this following expression. So integral from A to B in the exponential. So the third curve is interacting with the first one, and then the second one. Second one is interacting with the top one, and then the third one. So H3 subtracting H4, and then plus H2 subtract. Maybe it's the other way around. Yeah. This whole integral and then penalized by exponential to the minus. So the way you should view it is as follows. You should view this expression in this bracket as the energy cost. So the more the curves with larger index go above the curves with the lower index, then the more the energy cost is. So then the less likely for such a configuration is. And then the picture what it implies is as follows. So locally, you should think of the curves in the KPZ line ensemble just as Brownian motions. And moreover, this scenario is more likely. So the curves tend to be ordered instead of being just disordered. Okay, so under this observation, now I'm trying to convince you that the star is in Y star is what we expect to be true. Okay, so because the KPZ line ensemble, they look like Brownian motions, I'm just going to replace the curves in the KPZ line ensemble by IID Brownian motions. So what I'm doing here just to replace this XT here by this Brownian environment. It's an IID collection of Brownian motions, and then you just consider the same event. And now if we look at this expression, it actually has this interpretation, chaos interpretation in terms of this semi-discrete polymer across the Brownian environment. So what we can do here, so because in this regime, it goes to the narrow wedge solution of the KPZ equation, and then in the regime we consider before X is fixed, so equivalently, you can view this as an intermediate disorder regime such that the temperature beta is very small. Its inverse temperature beta is very small. It's of order n to the -1/4. And then, yeah, by the facts for this polymer free and semi-discrete polymer free energy, when if beta is very small, then we only need to look at the first order of the chaos expansion. So then you do get this normal distribution. And then if you plug this into here, that's why you get n to the 5/2. Okay, so what I'm saying here, if you consider IID Brownian motions, this is indeed a very unlikely event. And then because the KPZ line ensemble, locally they look like Brownian motions, so that's why star is likely to be true. Yeah, also there's something I want to share about this result. So this is actually the first paper I read, first probability paper I ever read. So that was back in 2017, and also when I first entered the field. I was reading this paper at this PCMI summer school, and also listening to the wonderful lectures by Jeremy on the KPZ fixed point. Okay, yeah, so now, yeah, so what I just told you is not a proof, right? So then how can we make that, turn that into a proof? And it will be much easier. KPZ line ensemble, they're indeed ordered. So in the sense that the first curve is hello, yeah, in the sense that the first curve is above the second one, and second one is above the third one. So it will be a much it should be a much easier problem to do. The question I want to raise today is whether the KPZ line ensemble is indeed ordered. So the evidence we saw earlier, that's in favor of that. And this is also how people usually draw the KPZ line ensemble. So and now I'm wondering, is this how people should really draw the KPZ line ensemble? So let me tell you why. So the supporting evidence is the Gibbs property. It tells us that this is the scenario where that is of higher weight. But now let me tell you a strong evidence which is against that. And that is through the O'Connor line ensemble.
When you say order, you don't mean that it's everywhere order, you mean order is expected.
Yes, so I'm being very loose on that. So order in with a high probability. With reasonably high, you don't have like it doesn't have to be probability close to 1, just like a probability, a positive amount of probability. Also, you can just say stochastic domination. For example, if you look at a one-time slice here, the first particle is stochastic dominate, the second one, so on and so forth. Okay, yeah, so now let me tell you the evidence. So if you consider the O'Connor line ensemble, it's just the polymer free energies if your environment is the IID collection of Brownian motions. And turns out for the O'Connor-Ewell ensemble is completely out of order at the initial time. So and they're not well defined. So the polymer free energy. Yeah, so the Y1 is the value of the first particle. You can see that if you let J to be 1, this is n minus 1 times log T. When T is small, this is a very negative quantity, and then altogether is very negative. But when J is equal to capital N, this is a minus n plus 1, which is negative, and the negative very positive. So you can see that the particles are actually at the top. No, is the first particle here. And then to the this is how they go to when T is going to 0, how they the first few particles blow up to minus infinity, and then the lower particles blow up to positive infinity. So that means in the beginning, the particles are totally disordered. And this is also not going to improve if you let the system evolve for a longer time. So if we look at the time where we do see the KPZ equation, that is the diffusive scaling. And even at this case, you can see that Y1, so we can compute the symptomatic behavior of Y1 is of this size. And then Yn is that one. So you can see that Y1 is a lot less than Yn. So, and this is basically all I know about how it should behave. So if we know Y1 here, Yn is here, so I really don't know how I should draw the point in the middle. So there are two scenarios I can think of. One is that the points are totally disordered. So because eventually you need to go up, so at some point you start going down. And then one scenario is, for example, this is just 0, so you just keep going up. The other one is just the first few particles. The first few lines, they're going to be ordered. So the difference between these two scenarios is in case 1, if you take the diffusive limit to the KPZ line ensemble, then because the top curves they're ordered, that implies the KPZ line ensemble is going to be mostly ordered. But if it's the scenario of case 2, that means the KPZ line ensemble is not going to be ordered. So now I'm not sure which one is gonna be the case. And yeah, so this seems like a bad news. But I do have some good news to share with you, which is that even though we don't know if it's ordered or disordered, but we can control how disordered they are. So it's not going to be that disordered. And this function here is just measuring the magnitude of the disorderness. And there's the result we have. So the essential point of this result is the constants C and alpha here, they're universal constants. They don't depend on the boundary data. So even as worse as the O'Connor-Ewell case, they are totally disordered and going to infinity in different directions. We can still control the magnitude of disorderness as long as you go to the interior a little bit. Any question regarding the statement?
That's true for completely arbitrary assumptions about the beginning and end point of random curves.
Can you see that question one more time?
Is that completely valid with arbitrary beginnings and end points for the end curves?
That's a good question. It's completely independent of the endpoints, but it does depend on the boundary, the boundary curve. So if it's a finite system, then we don't care about it. But if it's an infinite system, if we are looking at the disorderness of first K curves, we do need information on the K+1 curve.
These random curves are defined between -n and n or something? where is that? N is just the number of them, where is the boundary data being specified?
Oh, so for the velocity, I only consider finite interval, but it can be either finite interval or infinite one.
So Ivan, you have n curves and then this order function is defined in terms of them. So there's W1 up to Wn, that's where the n comes in.
Does that answer the questions? Yeah, so the message is that even though the initial boundary condition, they can be totally disordered, as long as you let the system a little bit of time, the magnitude of the disorderness can be controlled. And also in terms of the scale here, this log n is optimal because we already saw log n in the O'Connor-York case. Unfortunately, the constant C I can get here is not optimal. So if I can get a C which is less than 3/2, then that implies the star. So right now the C I got is like a 10. Yeah, to be sure, because when I saw that I could not get to 3/2, then I just gave up keeping track of how optimal I can get.
So the boundary is on -2 and 2, or you have some space to come in first?
Yeah, you have a buffer region, so yeah. Yeah, probably you can see better if I give you the if I show you later how the framework works. So let me first give you some heuristic why that should be the case, and it can be can view from this ODE computation. So let's just consider a scenario you have two curves, and then the first curve is just a straight line, which is W1 here. And then this is the Euler-Lagrange equation for the most likely trajectory. And this is computed through by combining the Dirichlet, the Brownian canonical cost, and also this Gibbs resampling Hamiltonian. And yeah, so this W1 here, or W2 here, this straight line. And then you have this initial disorderness. And then you can see that if you compute the solution to this ODE, it will rise up. And now you may wonder if I let this disorderness to go to infinity, that means we'll let the starting point to be further and further down. And what it can be seen is that you do have a limit shape. So even though your disorderness at the initial time is infinite, you still need to rise up. And that is a deterministic case. And if you turn on the randomness, this is what you will see. So you can see that as long as you let it evolve a little bit of time, this disorderness is going to be controlled. And then
You get a description for this in the Brownian case?
the
What
limit
is-
shape.
But what is the law, like in this example, what is the law of the blue thing?
So there is a ODE theorem tells you that you do have a limit shape, but doesn't have a closed formula for the limit shapes. Yeah, so this is yeah, I'm going to consume. This is the last slide. This is the framework how I do that is a infinite iteration, and basically the odds as a follow. This is the interval from -2 to 2. Eventually, we want to control the disorderness, the magnitude of disorderness from interval -1 to 1. And what we're going to do is define a next sequence of intervals. So we can do it at the start of the line, like this. And then every single time you improve a little bit. And what we need to do is we can finish this iteration in finite amount of time, and then get enough improvement. And this is what we can achieve here.
Are you saying it substitutes for condition star in terms of something that then allows you to deliver the theorem statement?
Yes.
Oh,
Yeah, also if I can get say for example, is equal to 1, then star, I can get a star, and then the construction of the fundamental solution from the KPZ ensemble will hold. Yeah, okay, so yeah, this is the end of my talk and thanks everyone.
Question. If you use the ODE heuristic, what's the value of C here? Is this like a reasonable thing to ask or?
I can show you how I, so. What, this, say it's at most a 10 I can get, and I think I can get to, up to 3. I didn't keep track of that. I see that I cannot get 3.
But I'm just wondering, like, if you just use this heuristic, that basically what you have is a solution to this ODE plus the Brownian curve on top of that. Does this, do you have some heuristic that tells you that C should be less than 3 halves, or? And like the worst case scenario for C is less than 3 halves?
Yeah, from that heuristic, I do believe C is less than 3 halves, but I don't have a, on top of my head, I don't, have the exact value of C should be, I can, yeah, show you later.
Regarding my curve, so not just from diffusion with some form of exponential grid, so it comes in from minus infinity to finite time, and then in addition to again go to tools, I do which comes from over this from infinity.
Right now the diffusion. If you could have thought that coming from minus infinity or plus infinity depending on the particle, I don't think it is completely infinite. So, let's find greater function is the following. And there's one special solution I wish we could function. And it's only the fundamental of the evolution for that, the equation and the evolution and so on. So I'm going to try to right.
I wonder if you're talking about this group, so it's just one guy.
Oh,
I think the question was in your heuristic, when you said just take a single Brownian motion and then the 0 for the second curve, what happens if delta goes to minus infinity? There's a nice description.
yeah, so I found a ODE paper which tells me that there is a limiting curve, but it doesn't tell me it doesn't say that whether there is a closed form of
But
the.
not even the rand, like, not the deterministic thing, but the. Somehow you're thinking about a single Brownian motion that has this exponential potential with respect to a fixed curve that's 0. Now you're taking the starting point to minus infinity. Like the question is just what is the description of the limiting random process? We can talk about it.
I believe that should be fluctuating around this limit shape. So if
Oh, you should, I mean, it should be relatively expressed. So, you don't have to count the second, you probably have to put it in the grid for the that's the time and two conditions to go on.
okay, yeah, let me try that later.
Questions? So let's thank Xuan.